So in this tutorial we're going to look at the technique of sampling, and we're going to use two kinds of sampling. We're going to start with just ordinary random sampling where we're taking a percentage or a fraction of a population that we want to study. But the second thing we're going to do is look at stratified sampling, which is a little bit different. That's when you do have, again, a census like this, but you have two or more groups that are identified within that as needing to be proportionally represented. First of all, we're just going to look at selecting a sample, a data set from this larger population that we want to study. So the first thing I want to do is look at the data set that I've got here, the whole population, and I want to think about how many I want to have in my sample. Now, sample should have at least 10%, and if I look at 9 columns here, and how many? We've got 40 rows, so we've got 360 in our total population. So we've got a census of 360 domestic cats, and they've been weighed somehow to give us their mass in pounds. Okay, now if I want to select then a reasonable sample, 100 seems to be a reasonable sample. 100 is well over 10%, and also 100 is going to be a nice figure to work with. So our aim is to select randomly 100 of these values. Now, to do that, a good idea is just to turn our sheet of paper around so that we're not worried too much about the values at this stage, because all I want to do is randomly select, as it were, 100 objects. So just treating these values as objects. So if I turn my sheet of paper around, that's going to make life a little bit easier, because I'm going to be ignoring these numbers and just thinking of them as things. It's also, though, easier from the point of view of counting, which is going to be important. It's quite a laborious thing to select 100 things from 360. So I want to make that job as easy as possible. And if I have it this way, I've now got 40 columns, and 40 is divisible by 10, and in fact divisible by 5, and that's an easier way to count. So counting in 5s and 10s is much easier than counting in, say, 9s. Okay, so to make that easier, I'm actually going to draw a grid over my census. So I've got 2, 3, 4, 5, so draw a grid here, here, okay. So just some vertical lines. That's going to make it easy to count. So I now know I've got 5, 10, 15, 20, 25, 30, 35, 40. So that this must be my 40th entry. So if I count up in 40s, I've got 40, 80, 120, 160. This must be my 200th entry. And that's a nice point as well to be aware of. So I'm going to draw a horizontal line across here. Okay, now, how do I randomly select 100 of these entries? Well, what I can't do is roll a dice and just go through each of these rows, for example, because who's to say that I should have a sample from each of these rows? In fact, that's what we're going to look at when we look at stratified sampling. But in this case, I want a truly random sample from here, which might be bunched either towards the top or towards the bottom or towards the middle. So I can't operate in that kind of way. What I'm going to do is actually treat the whole thing as 360 numbers. So I need to generate a number from 1 to 360. Now that can be done in a calculator, and it's, I guess, not the example and not the technique that's recommended in a lot of textbooks. They tend to use this button here, the random button on a Casio calculator, which will give you 3 random digits. But in this case, with 360, there's going to be an awful lot of wasted examples. So if I get 3 random digits such as 777, let's say, then I'm going to have to ignore that and keep pressing that equals button. That's going to be really hard work. So instead what I'm going to use is the random integer button, which simulates a dice. So if I press now the random integer button using the red alpha key, it wants two parameters. So I'm going to say 1 to 360. So 1 and then comma 360. Close my brackets. Now when I press the equals sign, it should just give me a random number as if I'm rolling a 360-sided dice. Okay, so let's go for the first number. Press the equals button, and now we've got 92. So I now know this is 40th entry, 80th. This must be the 90th. So the 92nd entry is this one here. Okay, that's the first one done. Press the equals button again, and I get 280. Again, I know that's 200, 240. So this must be the 280th entry. Okay, now I'm going to speed this up now. I've got 100 to do, but I'm going to use exactly this method here to generate a random sample. I'm going to do them 10 at a time. So we'll have 10 sections here. So we're going to do 10 at a time. And when I've done 10 of those 10s, then I'll have my 100 example. So let's just do that. Okay, let's start. Okay. So that's halfway. And finally, there we have it. Okay, so that's a random sample of 360 data entries. And the point of doing this is then to take those numbers and I guess type them into something like Microsoft Word, into a table, reorder because we want our data to be ordered, and then I should have a nice sample of 100 entries. I'm just going to now do that and then write it up in a grid and show you the final result. Okay, so it looks something like this. And we can see that we've got a range then from 3.8 to 18.6. So that gives us our range. If I subtract 18, let's actually just write that down. So the range is 18.6 subtract 3.8. So maybe I want to just use a carry method here. So 7. And so 3 from 7. So 14.8. So my range is 14.8. I can calculate the mean. The mean average is when we add all these figures up. We won't be able to do that in one line, so we'd have to add all these together, we get totals for each row, and then that will give us our mean average. Add the totals and divide by 100 to get the mean. And we might also be interested in the mode. So that's the most frequent number. And finally in the median. So the median we can do now. The median would be, well, between the 50th and the 51st number. So this is the 50th and this is the 51st. I guess the median is going to equal 8.95. Okay, so that begins our analysis of the data. But what I want to do before I go on to do that, and I'll do that in a separate video, is actually look now at stratified sampling. So this time what I'm going to do is have a look at, I'm going to look at some lottery balls instead. So let's just show you a pattern of lottery balls that I'm laying out in rows so they're easy to count. So again, I've got 360 in total. Okay, so the total is the same. But this time, what I'm going to do is make sure that the reds and the blues and the greens are all represented in proportion. So they're proportionally represented. Now you can see that in an animation which goes through an algorithm that will take a proportional number of reds, a proportional number of blues, and a proportional number of greens. What we're going to do is select 90. So we want a stratified sample. So stratified sample this time of 90 of these lottery balls here. We might also want to think of them as, in fact, let's think of a sports centre example. So this group here, let's call it A, might represent adult males, B could be adult females, and C could be children. And then you can see why you might want to do this, so that we don't have, for example, a random selection might be bunched in one direction, and therefore, maybe the children aren't properly represented, or the women, or the men. So stratified sample will keep those proportions, and a typical exam question might ask, well, how many are we going to randomly select from A, B, and C? So let's do that calculation now. Now, the very first thing I want to do is count how many we've got in A. So we've got rows of 20 here. So we've got 20, 40, 60, 80. So we've got 80 altogether. So A is 80 out of 360. B, well, the fraction for B is going to be 20, 40, 60, 80, 100. 20, 40, 60, 80, so 180. 180, take away, so 200 to here, take away that 5, 195. Finally for C, what have I got? 20, 40, 60, 85. And whenever you do a count like this, it's a good idea always to do a check. So let's use a different colour here for our check. So we're going to add 80, 195, add 85. Let's go from right to left, so 10, carry the 1. We've got 8 and 9, 17, 25, 26. And the 1 and 2 makes 360. Okay, so we've added that up correctly. What we now need to do is use these fractions to multiply by the sample size that we want. So we want 80 360ths, or 8 36ths if you like, of 90. So times 90 for each of these fractions. And this immediately gives us a nice cancellation, because 90 goes into 364 times, and we can do that for all of them like that. Okay, so all we need to do is divide the 80 by 4. 80 divided by 4 gives us 20. 195 divided by 4 is a bit trickier, so 4 into 19, well, goes 4 times remainder 3. So if I put a little 3 here, so that's going to be 4, 40 something. So 4 into 35, well, 4 8s are 32, so I've got 8, remainder 3, 3 quarters then, so 48.75. Okay, what about this sample? Well, my fraction here, 85 divided by 4, 4's into 80 we know is 20, and 4's into 5 is 1.25, so 21.25. Okay, now what we need to do is round a couple of these examples, because, of course, we're dealing with discrete data, whether it's lottery balls or the people in the sports centre, we can't have a fraction of a person or a fraction of a ball, so we do want whole numbers here. We just need to be a little careful when we're rounding. If, for example, I had 48.5 and 21.5, if I've rounded both of those up, which people tend to do, we're going to end up with too many balls. So we'd need to round one of them up and one of them down. In this case, it's going to be fairly straightforward, but we need to be careful that our total will still add up to 90. So we've got 20, remains as 20. The 487.75 becomes 49, and we're going to round this one down to 21. So the answer is that the reds, or the A group, we need to randomly select 20, from the B group 49, and from the C group 21. But again, we're just going to do a check to make sure our total adds up to the 90. So 0, 9 and 1 makes 10. Let's just write a check here. To the 10, carry 1, 2, 4 and 2 is 8, plus the 1 gives us our 90. So we're going to say these answers correct. Okay, now finally you might want to sample a population simply to find out how big that population is. So this is a common technique used in biology and the natural sciences. It might also be used on in an everyday kind of situation like this, where you're trying to estimate a number basically that's difficult to find. So the number of sweets in this jar, for example. Now we can generalize this mathematically by thinking again of our lottery balls. So this time what I've got is, well, 300, well it is, no, my mistake, 624 lottery balls. So rather large population here that we haven't dealt with up to now. And what I'm going to do is I'm just going to take, I'm going to mark a selection of these balls. So I'm just going to mark a smaller number. So let's just mark a few. So any number really that I can count. So I've marked 20, 40, 60, what's this? 5, 10, 14, so it's 74 plus 4, 78. So my fraction of marked balls to the total population is 78 compared to the total population, which, as we said, was 624. Okay. Now if I simplify that fraction, I've got 1/8. And so I've got a clear idea of the proportion of marked balls to the total population. If I didn't have an idea of the total population, however, I could represent this algebraically. So let's just change this now as n. So I know I've got 78 balls. What I don't know is the total number of the population, which I'm going to call n here. So how am I going to find n if I don't know what that number is and I can't easily count it? Well, one thing you can do is take a sample. So we're going to take a sample now. Let's take 40 balls randomly out of this population. Okay, so we've taken 40 balls and we discover that 5 of them are marked. And I can just rearrange those so we've got the same sort of thing as we have here. So now I can say, by counting the smaller population, that 78 over n must equal, or theoretically will equal, 5 over 40. And if that is an equation, then I can rearrange it to find n, so I can get an estimate of the total population. Now that estimate is going to get even more accurate if I take more samples, because who knows, these 5 marked balls might be too many or too few. So let's now take another sample of 40. Let's just mark this n. first of all. So this is big N. So let's take another sample. There we go. And this time we've got 3. So let's take a third sample. This time we've got 7, now 6, and now 4. So we want to see if this 5/40 is a good, is going to provide a good estimate, is accurate in terms of reflecting the proportion of marked balls to unmarked marked balls to the total population, rather, in the whole population. So let's have a look. Let's see if we can average these. So if we take our first sample, 5/40. Our second sample, which is 3/40. So we've got a common denominator. We've got 7, 6, and finally we have 4. So if we add these together, we got 5/3/7 is 15, plus 6/4 is 25. 25/40, but we want to divide by the total number to get the mean. Okay, so if we divide by 1, 2, 3, 4, 5, then it equals 25/40 divided by 5 to get the mean. And 25 divided by 5 is 5. So again, we've got that fraction 5/40. So the 5/40 was in fact a completely accurate fraction. And so this 5/40 does equal 78 out of n. So this is going to give us a very accurate now estimation for n. Still only an estimation because we don't know whether further sampling would have changed this fraction. So how are we going to rearrange for n? Well, very simply, I'm just going to invert both sides. So if 78 to n equals 5 to 40, then n to 78 must equal 40 to 5. Therefore, n, big N, so the population size, out of 78 must equal 40 to 5. And therefore, n equals 40 divided by 5 is 8, and if I multiply both sides by 78, then I've got n equals 8 times 78, which if I work that out is going to come to our total 624. So that accurately estimates the population of this sample here. In practice, what you're going to have to do is take several samples just to be confident that this fraction is representative.